Hi all, in this class we can see what is a Galois field. So we already discussed that in a field, if the number of elements is finite, then we can call it as a finite field. And also we said that the number of elements in a field is called its order. So similarly, if a number of elements in a field is finite, then we can call it as Galois field, and it is represented as Galois field of Q. So that is Q is the Q consists of 0 to Q minus 1 elements. So the Galois showed that for a field to be finite, the number of elements should be p raised to n, where p is a prime and n is a positive integer. So if a field consists of finite number in such a way that the number should be expressed as p raised to n, where that p is a prime number and n is a positive integer, then that field is called as a Galois field. So simply we can say that a finite field is called a Galois field, and the number of elements in that field is called as its order. Generally, this Galois field are represented as GF of Q. That means Q means we have elements from 0 to Q minus 1, and its order is called as Q itself. And we are taking a non-zero element from this Galois field of Q. So now we can take a non-zero element as A. Then the power of A also a non-zero element of Galois field of Q. That means this A we can represent as A1, A raised to 1, A raised to 2, A raised to 3, etc. So that power also should be in this element. So that power also should be in this Galois field of Q. And the smallest positive integer n, for which A raised to n equal to 1 is called its order. So for an element A, if we are represented as A raised to 1, A raised to 2, A raised to 3, etc., then at a particular value, for example, if A raised to 3 is equal to 1, then that 3 is called as its order. So then after this 3, this power will repeat again. That means A raised to 1, A raised to 2, etc. will repeat. Then we can say that a field element is said to be primitive if its order is Galois field of Q is Q minus 1. For example, if a Galois field consists of 5 elements, then the order of this element, if we are taking an element A, then its order is also 5 minus 1, that means 4. Then we can say that is a primitive element. So if you are taking a Galois field of 5, that means it consists of 5 elements, that is from 0 to 4. Then if you are finding the power of any element, for example, if you are taking an element 2 and then we are finding it's 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. Then if 2 raised to 4 is 1, that means its order is 4, and that is equal to Q minus 1 itself. Then that element 2 is called as a primitive element. So that's all about Galois. So next we can see one example. So one example is Galois field of 2. So Galois field of 2 means it consists of 2 elements only. That means 0 and 1. And the 0 and 1 is a field that is closed under modulo to addition and modulo to multiplication. That means A operated on B should be a resultant. That A operated on B resultant should be an element in the group itself. That means that element should be 0 or 1 itself. So that is Galois field of 2. So remember, Galois field of 2 consists of only 2 elements, that is 0 and 1. Next we can see one example how we can check whether an element is a primitive or not. So for that we are considering a Galois field of 7. So Galois field of 7 means it consists of 7 elements, that is from 0 to 6. So whether an element in this Galois field is primitive means if the order of that element should be equal to Q minus 1. Here Q is 7, so Q minus 1 is 6. That means for that element, if that element is A, then A raised to 6 should be equal to 1. Then we can say that that element is a primitive element in this example. So we can see that. So our field elements are 0, 1, 2, 3, 4, 5, 6, etc. So we need to take all the non-zero elements to check whether it is a primitive element or not. So first we can take a equal to 1, then 1 we need to find the power of a, that means 1 raised to 1, 1 raised to 2, etc. So for this 1, if we are finding this 1 raised to 1 itself as 1, so the smallest positive integer for which a raised to n is 1 is called as its order. So for a equal to 1, the n equal to 1 itself, so its order is 1 itself. So we can say that it is not equal to 6, that means it is not a primitive number. Next we can take 2, so then we need to find its power, that means 2 raised to 1, 2 raised to 2, etc. So 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8. 8 is more than this 7, so we need to find what is modulus value, that means we need to take the remainder. So 8 minus 7, we need to find 8 minus 7, so you will get it as 1. So 2 raised to 3 is equal to 1, then order of 2 is 3, so it's also not equal to 6, so we can say that 2 is not a primitive element. Next we can take 3, so we can find 3 raised to 1, so 3 raised to 1 is 3, then we can find 3 raised to 2, 3 raised to 2 is 3 into 3, so 3 into 3 is 9, so 9 minus 7 is 2. So next we can find 3 raised to 3. So to find this 3 raised to 3, we already found what is 3 raised to 2, that is 2. So we can find 3 raised to 2 into 3 as 3 raised to 3. So that means 2 into 3. So you will get it as 6. Then 3 raised to 4 is 3 raised to 3 into 3. So that means 6 into 3. 6 into 3 is 18. So 18 is more than 7. So you need to find 18 minus 7. So it is 11. 11 minus 7 is 4. Then 3 raised to 5 is 4 into 3, that is 12 minus 7, that is 5. Then 3 raised to 6 is 5 into 3, that is 15. 15 minus 7 is 15 minus 7 is 9. 8. 8 minus 7 is 1. So we can say that 3 raised to 6 is equal to 1. That means the order of this element is 6, n equal to 6 itself. So this q minus 1 is also 6 itself. So if the order is equal to q minus 1, then we can say that that element is the primitive element. So we can say that 3 is a primitive element. So this way we can find whether an element is in a field is a primitive element or not. So of this, the remaining element like 4, 5, 6, you can check whether it is a primitive element or not. So this way we can find whether a number is whether an element in a field is primitive or not. Next we can see some example for this GALOIS field. So first we can see the common GALOIS field we used in cryptography as well as in information theory and coding. So that is GALOIS field of 2. So we already said that in GALOIS field of 2 it consists of only 2 elements, that is 0 and 1. That means its order is 2. And basically it is defined for 2 operations like addition and multiplication, and for this multiplication 0 element is not considering. So we can see how we can do this modulo 2 addition and modulo 2 multiplication. So we have 2 elements and 2 operations, so we can see how we can do this modulo 2 addition and modulo 2 multiplication. We already said that modulo 2 addition is simply XOR operation. So we can see that 0 plus 0 is 0 itself, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. That is simply addition. So if the symbol addition is simply XORing of these 2 digits. So in addition to this, we can do this using this expression for modulo 2 addition, or modulo m addition is remainder of I plus j by m, where m is the number of elements in the field. And this we need to find what are the elements we need to add, that is I and j. Then we need to add I plus j divided by m, we need to find. Then the resultant is not important, the remainder is only we need to use. So for modulo m addition, the remainder of I plus j by m is needed. And similarly for multiplication, modulo m multiplication means remainder of I into j by m, we need to check only the remainder. So in this GALOIS field calculations or modular arithmetic, we need to use only the modulus value and we need to take the remainder value only. So modulo m addition means remainder of I plus j by m. Similarly modulo p multiplication means remainder of I into j by P. If it is modulo P, multiplication. So remember, modulo M addition is I plus J, remainder of I plus J by M. Modulo P multiplication is remainder of I into J by P. So we are concentrating on only the remainder. The resultant is not at all important. Only what is the remainder after division. That's only we need to represent in this column. So we can see what is the addition table and multiplication table. So addition table, we have 2 columns and 2 rows. That's elements are 0 and 1. Then we are going to add remainder of I plus J by M. So here M is number of elements in the field, that is 2. So 0 plus 0 by 2. As we know, 0 by 2 is not divisible. So the answer is that I plus J itself. So 0 itself. Again 0 plus 1 by 2 is 1 by 2. Again 1 is not perfectly divisible by 2. So the answer is I plus J itself, that is 1 itself. Then 0 plus 1 by 2 is again 1. 0. 1 plus 1 is 2 by 2. So if you are divided 2 by 2, you will get the remainder as 0. So the answer is 0. So we can say that for this modulo M addition, our table is 0, 1, 1, 0. So that's the modulo M addition. So remember, remainder is only we needed. And similarly for multiplication also, remainder of I into J by M. So we can use this easily by remembering the equation. If I plus J or I into J is less than M, then you can write the table. You can fill the table as I plus J or I into J itself. Then if I plus J or I into J is equal to M, then you can fill the table as 0 itself. And if I into J or I plus J is greater than M, then you need to find I plus J minus M or I into J minus M. Then that will be the result. If it is again greater than M, you need to do this calculation one more time. That means you need to do I plus J minus M one more time, or for modulo P multiplication you need to do I into J minus M one more time. So that's the way we can find it easily. So that's easy way to find this modulo P multiplication and modulo P addition. So that's why we can find the addition. And multiplication also, 0 into 0 is 0. So this for multiplication, if it is one of the element is 0, then the resultant is always 0. Then another another element is only we need to consider. So 1 into 1, its result is 1 by 2, so it is less than 2. So the answer is I into J itself, that is 1 itself. Next we can find what is the inverse, additive inverse as well as multiplicative inverse. So we can find it easily using this table itself. So for addition, we know the for identity element for addition is 0. So you need to mark all the zeros in the table. So where the result where the addition table is there. So in that table you need to mark all the zeros in that table. So we can see that for first row, that is for element, if the field element is 0, the 0 is coming for 0 itself. So the additive element inverse of 0 is 0 itself. And for 1, we can see that this the 0 is coming for 1 itself. So the additive inverse of 1 is 1 itself. And for finding the multiplicative inverse, you need to mark all the ones in the table. So we can see that for non-zero elements only this multiplicative inverse is defined, and for 0 element we didn't have any multiplicative inverse. So you only concentrate on non-zero elements. So here the non-zero element is 1 only. So for for this 1 we can say that the 1 is coming for 1 itself. So the multiplicative inverse of 1 is 1 itself, and for 0 there is no multiplicative inverse. So this way we can find the Galois field of 2. And next we can see one more example, that is Galois field of 5. So the Galois field of 5 means it consists of 5 elements, that is 0 to 4. So we can see that the elements are 0 to 4. Here also we are defined the operations addition and multiplication. So first we can prepare the addition table. So for that we can write all the elements 0, 1, 2, 3, 4 in column and row wise. Then first we are going to add the elements. First our element is 0, 0, then 0, 1, then 0, 2, then 0, 3, then 0, 4. So if it is added 0, 0, you will get 0. It is less than 5. So we can write 0 itself. Then 0 plus 1, 1. Then 0 plus 2, remainder is 2. 0 plus 3, the remainder is 3. 0 plus 4, the remainder is 4. And next row, the 1 plus 0, the remainder is 1, 1 plus 1, the remainder is 2, and 1 plus 3, 1 plus 2, the remainder is 3, 1 plus 3, the remainder is 4, but for 1 plus 4, the resultant 1 plus 4 is 5, 5 by 5 is resultant 1, but the remainder is 0. So we can see in that table, if you are added 1 and 4, the remainder is 0. You only concentrate on remainder. Then 2 plus 0, 2, then 2 plus 1, 3, the 2 plus 2 addition, remainder of 2 plus 2 by 5 is 4 itself. Then 2 plus 3, the result is 5 by 5, remainder is 0. Then 2 plus 4, it is 6 by 5, remainder of 6 by 5 is 1. 6 by 5 we can easily find using the equation 6 minus 5. So its result is 1. Then 3 plus 0, 3, 3 plus 1, 4, 3 plus 2 again 5, 5 minus 5 is 0. Then 3 plus 3, 6, 6 minus 5 is 1. Then 3 plus 4, 7, 7 minus 5, remainder is 2. Then 4 plus 0, 4, 4 plus 1, remainder is 0. 4 plus 2, remainder is 1. 4 plus 3, that is 7. 7 minus 5, remainder is 2. 4 plus 4, 8. The remainder of 8 by 5 is 3. This way we can find the modulo 5 addition table. After finding this, you can mark all the zeros in the table, so then you can easily find what is the additive inverse. So for 0 element, the 0 is coming for 0 itself, so the additive inverse of 0 is 0 itself. And for 1, the 0 is coming for 4. So the additive inverse of 1 is 4, and for 2 the 0 is coming for third column, that is the additive inverse of 2 is 3, and the additive inverse of 3 is 2, and additive inverse of 4 is 1 itself. So this way we can find the additive inverse. Next we can find what is the multiplication table for this Galois field of 5. So for that we can write for 5 columns, that is from 0 to 4, and 5 rows, that is from 0 to 4. Then we can find what is the remainder of I into j by m. So here I into remainder of I into j by 5. So for 0, all the elements, if you find the multiplication, you will get it as 0. So only non-zero elements we can find. So 1 into 1, 1. 1 into 2, the remainder is 2 itself. 1 into 3, the remainder of 3 by 5 is 3 itself. Then 1 into 4 is 4, the remainder of 4 by 5 is 4 itself. And the next row, that means third row, is 2 into 1, that's 2 itself. 2 into 2 is 4 itself. 2 into 3, we know that remainder of 6 by 5. Remainder of 6 by 5 is 1 itself. That means 6 minus 5, that is 1. Then remainder of 4 into 2 is 8 by 5. Remainder of 8 by 5 is 8 minus 5, that is 3. Next is fourth row, that is 3 into 1, 3. 3 into 2, again 6. Remainder is 1. Then 3 into 3 is 9. 9 minus 5 is 4, so the remainder is 4. Next is 3 into 4, that is 12. So remainder of 12 by 5 is 12 minus 5, that is 7. Again it is greater than 5, so you need to do one more time, that is 7 minus 5. So you will get it as 2. And the last row is 4 into 1 is 4. 4 into 2 is 8. 8 minus 5 is 3. So the remainder is 3. And 4 into 3 is 12. So 12 minus 5 is 7. 7 minus 5 is again 2. So the remainder is 2. Then 4 into 4 is 16. So you can do it as 16 minus 5. It is 11. 11 minus 5 is 6. 6 minus 5 is 1. So the remainder is 1. So this way we can find the multiplication table. Next we need to find what is the multiplicative inverse. So to find this multiplicative inverse easily, you round all the ones in the table. So for non-zero element only this multiplicative inverse is defined. So for 1 we can see that the 1 is coming for 1 itself. So the multiplicative inverse is 1 itself. And for 2 this 1 is coming for 3. So this multiplicative inverse of 2 is 3. And for 3 the multiplicative inverse is 2. And for 4 the multiplicative inverse is 4, because for last row the multiplicative for last row the 1 is coming for last column, that is fourth row. Fourth column is 1. So we can say that the multiplicative inverse of 4 is 4. So remember, the multiplicative inverse is defined for only non-zero elements. So this way we can find what is modulo P addition and modulo M addition and modulo P multiplication, and how we can find the additive inverse and multiplicative